Okay, so here's where we are. So we came up with this integral. You have to evaluate everything at the boundaries. We have this function of time, so you have to evaluate that at both of the time boundaries. You're used to time, everyone's kind of used to time functions when you evaluate them at a boundary that's 0 going away. But because this is an exponential, you have to take into account that that lower time boundary gives you a number. And that's what I left off before. So 909.2, that's the two 454s added together, minus 454.6 e to the minus t over 20, minus 45.46 t. And now we're trying to find the zeros of that. Wow, the next problem is going to go a lot more smoothly than this one. So I'm going to do it here. If you can think of a way to solve that, do it, but I'm just going to look at a graph. So the function is 909.2 minus 454.6 times e to the power of negative t over 20. Minus 45.46 times t. And this time it starts out with the volume that it's supposed to start out with, so that's good. Looks like it takes more time than that. So. 15 days, okay. What's complicated about it?
It just has a written formula as the intercept.
Okay. Yeah, okay, I gotcha. Well, right. So what I get is an intercept between 15.3 and 15.4 days. So if you graph that function, it hits 0 volume around 15.4 days. Okay, well that sucked. So let's do another one. Okay, so this one, this is number 4 from the same conservation of mass set of problems. So this one says, so you have a cylindrical tank. There's a cross-sectional area of 1 square meter. So it's a tank with this 1 square meter cylinder, and it's being drained through a duct at the bottom, and it gives you the cross-section of that. And it tells you the velocity of the water coming out of the duct according to the height of the tank. So it tells you again how much, what's the mass of the water that's in there to start, and how long will it take until the tank has a certain amount. You know that you can relate the height of the water to the mass because you have the cross-sectional area, so you can come up with the volume of the water and then multiply by the density. And so that's going to be the relationship, how we get between those two variables. Okay, so this looks like, so you have a tank like this. Here's the water level. And that has an area of 1 meter squared. And so the mass of the water is equal to, the area is 1, so the area times the height, which is, we're calling Z in this problem, times the density, which is 1,000 kilograms per meter cubed. And so the mass function, the mass that you have in that control volume is 1,000 Z. And so the key thing that we're going to use to do this problem is that dm dt is ddt of this thing which is, 1,000 dz dt. Okay, so we'll come back to that. The area of this spigot that the water is coming out of is 3 times 10 to the minus 4th meters squared. And the speed of the water coming out of there is 2gz square root. The density is the same. This is incompressible. And so you can figure out, the mass flow rate that's exiting. We're used to that being A times the speed divided by the specific volume. That's the same thing as the density times the area times the speed. And so that's equal to, so that area times 1,000 times the square root of 2g, you end up with this being 1.329 z to the 1/2. Well, the continuity equation, the conservation of mass equation says dm dt is equal to the mass flow rate in minus the mass flow rate out. This is 0, there's nothing coming in. And so we can just put these two pieces together. So 1,000 dz dt is equal to 1.329 z to the 1/2. Okay, any idea how to solve this differential equation? This is the most important, like, there's a million different techniques for differential equations, but this is a simple one, and it's also the one that comes up the most in mechanics classes. Separation of variables. So just get all the z's on one side, all the t's on the other side. All right, this is 1,000. Multiply both sides by z to the negative 1/2. So 1,000 z to the minus 1/2 dz is equal to 1.329 dt. And now you can integrate both sides of that. This one, I left off this negative sign. There's a negative sign over here. And so integrate the left side and you get 2,000 z to the positive 1/2 evaluated from state 1 to state 2. And that's equal to negative 1.329. This one we're doing over time, so this is going to be from time equals 0 to time t. And we're going to try to find that time t. So now we're going to have to figure out what these, before we can substitute in for z, we need to figure out what our starting and ending heights are. We're given that in terms of masses. So to find these start and end heights, we'll use the fact that mass is equal to 1,000 z. So for state 1, it's, what did it say it started out with? 2,500 kilograms. So 2,500 is equal to 1,000 z. And so z1 is 2.5. That's meters. And state 2, at the end, it says that it, so in the wording of the problem, what it says is how long is it going to take for the mass to reach 900 kilograms. So for the second one, 900 is equal to 1,000 z. And so z2 is equal to 0.9 meters. And so 2,000, you can do this as 2,000 square root of 0.9 minus square root of 2.5. And that's equal to negative 1.329 t. And then solve for t. And can you plug that in? You get like 951 seconds, something like that.
– 951 × 10⁻⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻
So 952 seconds, and he asked for it in minutes, so divide by 60, and you get about like 15.9 minutes, something like that. That problem is, just like the other one really, except I guess there's sort of two tricks. The first one, the one that's really like relevant for something you would see on tests and stuff, is coming up with the relationship between the height and the mass, and then whether you recognize how to do that differential equation or not, that's sort of beyond what would ever be on a test or anything, although that is a really useful kind of differential equation to recognize. It'll come up a lot in your life. Any questions about either of those? Let's do a control volume one. So this is control volumes part one. And this is number two. And this one is a nozzle. So there's a starting pressure of 2.07 times 10 to the 6th Pascal. And a starting temperature of 315 degrees Celsius, 315.6. I think in this problem, everything was actually given in some other kind of units. That's why these are sort of funny numbers. So yeah, it's all in, the pressures are in pound force per square inch, and it's feet and seconds and stuff. So I just already did all the conversions. We're going to try to find the temperature of the exiting material. And it says it's starting out as steam, and we'll see what's happening when it comes out. It says that the starting speed is 30.5 meters per second. All right, this is a nozzle, so what's going to be happening at the exit with the pressure and the speed? Those are opposite each other. So if you can think of the speed, then the pressure is opposite. So so the pressure is going to be down and the speed is going to be up for a nozzle. So that would be backwards. So P2 is lower pressure, so 0.28 times 10 to the 6 pascals. And it gives the speed of 548.6 meters per second. And then we're trying to find the temperature. All right, well, first, I think the way to go with these is, you're going to see the first law for control volumes. Come up with that equation. Make sure you're not canceling anything that's not meant to be canceled in the problem. So I think it's a good idea to just start with the full thing and just do your cancellations yourself. So dE dt is equal to Q dot minus W dot plus, well, it's steady state, so I'm just going to write them as M dots to start with. They're going to be the same. Times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. It's steady state, so there's none of that. There's no heat transfer and no work. There's no change in height. And so what we're left with is just the standard equation for a nozzle or a diffuser that says, I usually try to remind myself to write it in whatever form is going to have both sides be positive. So that means that we're going to have VE squared over 2 minus VI squared over 2 is equal to HI minus HE. And we can fill in those speeds. So at the exit, that's so 548.6 squared over 2. And then minus at the inlet, that's 30.5 squared over 2. And that's equal to HI I wonder if it's Excel that's making this happen. Okay, so we're getting close to being able to solve for an enthalpy. And if you look at the inlet, we know the pressure and the temperature for this steam, so that means we can look it up in a steam table, the enthalpy. That'll let us calculate the enthalpy at the exit. And then we can do like sort of a reverse lookup in the table to figure out the temperature at 2, because we'll have 2 of those properties, and any 2 properties are enough to look up the other ones. So it's easier to look stuff up with pressure and temperature, but we can look it up with pressure and enthalpy and look up the temperature. All right, so we know this, or we know we're going to be able to get it. So now we'll look at the temperature and pressure. So P1 the pressure is 2.07 times 10 to the 6 pascals. Temperature is this. Neither of those are things that are given in the table. So we're going to have to do an interpolation to find those. So at the inlet, I'll say P1 is 2 megapascals. P2 is 3 megapascals because we're looking for 2.07. And then temperature 1 is 280, and temperature 2 is 320, because the temperature we're looking for is 315.6. Well, we're pretty close to just being at 2 megapascals and 320, so that would give you a pretty good approximation. But let me just do this one. Okay, so those are our points. And we can look up then the enthalpy at pressure 1 at pressure 1, temperature 1. And you get 2976.4 times 10 to the third joules per kilogram. And then look it up for pressure 1, temperature 2. And that's 3069.5 times 10 to the third. And then look it up for P2, temperature 1. And that's 2941 times 10 to the third joules per kilogram. And then the last one for P2, T2, that's 3043.5 times 10 to the third joules per kilogram. So now I'm going to interpolate first over P and second over T. So H of the P that I want, I'll just call that P. This is so this is at a pressure of 2.07 megapascals. And so that is, this should be T1. So that's 2976.4 times 10 to the third plus 2941 times 10 to the third minus 2976.4 times 10 to the third. divided by pressure 2 minus pressure 1. So that would be 3 times 10 to the 6 minus 2 times 10 to the 6. Times the P we want minus P1. So that's 2.07 times 10 to the 6 minus 2 times 10 to the 6. And the value you get out of that is 2973.9 times 10 to the third. That's joules per kilogram. Now do the same thing at temperature 2 for our desired pressure. So H for P and T2, I'm going to use the H we looked up at P1 and T2 and the H we looked up at P2 and T2. So 3069.5 times 10 to the third plus 3043.5 times 10 to the third minus 3069.5 times 10 to the third. Divided by 3 times 10 to the 6 minus 2 times 10 to the 6, and then multiplied by 2.07 times 10 to the 6 minus 2 times 10 to the 6. And for that one, you get 3067.7 times 10 to the third joules per kilogram. And now the last step is we'll use those two values we just calculated to interpolate over the temperature. So specific enthalpy at PT, so now this is at the pressure and temperature we want. Is 2973.9 plus the quantity 3067.7 times 10 to the 3 minus 2973.9 times 10 to the 3. And now we're dividing by the difference in temperatures this time, so 320 minus 280. Then multiplied by 315.6, our desired temperature, minus the lower temperature, the starting temperature. And we get this final value of the specific enthalpy of 3057.4 times 10 to the third joules per kilogram. Okay, so now we're going to go back to this equation. We sort of set this aside, but now we've calculated that H at the inlet, and we can use that to calculate H at the exit. So H at the exit, I'm just going to rearrange this, is equal to H at the inlet plus speed at the inlet squared over 2 minus speed at the exit squared over 2. And so that is 3057.4 times 10 to the third plus 30.5 squared over 2 minus 548.6 squared over 2 and you get an answer of 2.91 about times 10 to the third joules per kilogram. Okay, so now we calculated the enthalpy at the exit. That's not what we're asked for. We're asked for the temperature. So now we have to do this reverse lookup using the enthalpy and the pressure to find the temperature. So the question is, what's the temperature where you have a pressure of 0.28 times 10 to the 6 and an enthalpy of 3057.4 times 10 to the third joules per kilogram.
That's the enthalpy of it.
30 point, yes, thank you. H is 2.91 times 10 to the third.
And that 540, 48.6.
Mm-hmm.
Is that square root of 2, which is orders of magnitude bigger than the other values in that balance equation? For H at the exit is,
Let's see. So 548.6 squared. I mean, they're all big, you know.
yeah. That 3,000 e to the third.
Yeah, that's really big too. So I think this is right.
That works.
Okay, yeah. Okay, so look that up. I did get tired of interpolating and on that one. So if you, well, so let's look at the values in the table. So we're looking for that enthalpy we just calculated and 0.28 megapascals. This is water. We're looking for steam. So 0.3 megapascals is what they give us in the table. And we're looking for 2.907 times 10 to the third. So you can see that it's going to be somewhere in the range of 200 to 240 degrees. But you would have to do that again in a 3-step interpolation. So this would be another 3-step interpolation. But that temperature is somewhere in the range of 200 to 240 degrees Celsius. Oh, one thing. You can see how much more dependent this is on temperature than pressure. If you look at these values for like 0.1 megapascal, 0.15 megapascals, 0.3 megapascals, and look at the pressure differences for like 200 and 240, you can tell that interpolating over pressure isn't going to make much of a difference. You know, so you could also get a better approximation by just calling it 0.3 megapascals and just interpolating the one time between 200 and 240 degrees. Any questions about that? Okay. Next time I'm just planning to do a few more problems. We'll do some more of the ones on control volumes that I didn't have solutions for. And then also I want to go back and do a couple on ideal and incompressible assumptions. Just keep going through problems that there are no solutions for. This is all the stuff that's going to be on the test in a week. So, all right, that's it. Goodbye.